Today we're going to be talking about special function registers in our microcontroller. The main idea here is that when engineers are designing the chips that they're working with, they typically build around a CPU core of some kind. In this case, in this class right now, we're using the ARM core. What the designers at NXP have done, and what many designers do, is they license this core from some other company, in this case the ARM Holdings Corporation. They incorporate this design into their own proprietary peripherals and devices. So what they're doing is they've got a ready-built core and a tool chain for writing code for that core, and then they have to add on peripherals that specialize the particular devices that they're using. Typically, these peripherals take the form of memories, different clock settings, system configuration things such as watchdog timers, DMA modules, bit manipulation, any kind of low power modes and stuff like that, right? These are things that support the operation of the core. You need memory, you need clock configuration, you need power management, right? So these are the sort of core functionalities. On top of that, they then start to specialize these chips into particular areas that have good sets of peripherals that meet certain needs for different application areas. These might include things like timers for driving PWM or internal timing, communication interfaces that are specialized to particular applications. The ones we're using are very general, I2C, SPI, UART. They're kind of used all over the place. If you're developing something for the automotive industry, you're going to use a CAN bus, which is a different set of protocols. You're always going to have some kind of GPIO and maybe specialty controller software or controller peripherals for things like segment LCD controllers or display controllers or frame buffers, analog to digital conversion for reading analog values from sensors and objects like that. But all of these things are hardware that is built onto the chip around the microcontroller core itself. So these are things that are have to communicate with that core. The core is what runs the software. So the designers have to provide some interfaces from that core software to connect to the peripherals that are on the chip. The way they do this is through memory mapped hardware. So inside of that main memory thing, the core is always going to be accessing RAM or flash memory in some way. Flash memory is what stores our instructions, so we're probably not going to access those for peripheral hardware, but we will have some special function registers defined in RAM that instead of just holding a value, they still hold a value, but instead of just holding a value, they're also connected to physical components of the chip that either drive pins or some of the other peripherals like timers and analog to digital converters. It's basically the memory is the interface that we can write values to, right? Because that's what assigning a value to a location or a variable in memory does. We can write a value to it, and if we map those bits in that particular register to a piece of hardware, we can then control that hardware, right? And this is the model for almost all microcontrollers and how they work. So in this case, we have a register that's mapped to the physical pins of the chip, and when we write a 1 to a bit in that chip, a bit in that location, in that particular location in memory, that sets a particular pin high in the, that sets that particular pin voltage high and allows us, and that's connected to the outside of the chip, and that allows us to control hardware external to the device itself, right? So to make this easy for us, the memory locations are just numbers. They're specific memory locations inside the memory map of the processor, right? So the address is what is the thing that we need to remember to manipulate. The designers of the chip often do a lot of really good work for us and define macros that allow us to use these locations in memory as a named thing, right? In this case, we're calling it GPIO-D, GPIO, general purpose IO port D, and we're mapping that to a macro that dereferences the memory location. So we can now use this as a command or a variable that we can update, and that actually controls the hardware, right? So what that might look like is something like this. We do GPIO-D. The compiler replaces the macro with the dereference call of dereference memory location 6, And then as we're executing, this is a 1 shifted left 1, so we're going to put a 1 in the 2 to the 1 place, which sets the bit and turns on the LED that's connected to the pin on the outside of it, right? For the Freedom board, we have a piece of hardware called the MKL46Z header, and you can find this in your project directory in CMSIS and go down to MKL46Z4.h. And what's included in here is all of these memory mappings and the structure that the designers at Microchip have provided that give us standard interfaces for all of the different peripherals. So when you see a name of a peripheral object or a chapter in the reference manual, there's a section of this that defines the software interface for it. And we're going to be going over sort of how to find all this stuff and what it means and things like that in the next video. Right, but it's safe to say all of this stuff is contained in a place where you can go and look it up and see how it works. They don't give a lot of examples. We're going to be doing examples in class to figure out exactly what you need to do to make these things function. So the header file defines all of these macros and the mappings for names of things that we can use to the specific locations in memory. The reference manual defines how to use them. So what are the individual bits? What do they mean? How do we control what happens when we set a particular bit? What is the effect of a particular bit in a particular register? So here I've got GPIOD, the register is defined here, and the functionality in the reference manual is defined in the reference manual. In this case, it's in chapter 42.2.1, and this says each of these bits controls one of the pins, and logic level 0 mean in the register means that we're driving a logic level 0 or 0 volts on a particular pin. A logic level 1 means we're driving logic level 1. In this case, our board is a 3.3 volt board, so we're going to get 3.3 volts if we put a pin or put a bit in a particular space in this register. And each of the register bits corresponds to one pin on the microcontroller. So if I'm setting port D, bit 5, I'll set bit 5 in the register, and that turns on bit 5 on the microcontroller itself.